Swayam Prabha. Digital India. Educated India.
Now we move on to another part of this particular course, that is called Advanced Abrasive Machining Processes. We have completed already the conventional abrasive machining and finishing processes. Some of them are applicable for machining, some of them are applicable for finishing. Now exclusively what we see is advanced abrasive machining processes. Then once we complete this, then we move on to advanced abrasive finishing processes. Okay. So, this is a particular segment where we come across some of the advanced abrasive machining processes. As I said, machining process will deal with how much material removal that you have taken out from the workpiece. Okay. In a finishing processes, normally you see what is the final surface roughness that you have achieved. Okay. From that point of view, we will going to see here the machining processes using abrasives which are considered to be advanced. Okay. Some of the people call it as non-traditional machining also. Okay. So, there is no much difference between non-traditional machining, unconventional machining and advanced machining. Okay. So, since this particular course deal with abrasive based processes, that is why we are only talking about some of the advanced machining processes where abrasives are commonly used. We will see the overview of the today's lecture. Normally we start up with what are the advanced abrasive machining processes that we are going to study in this particular segment. Introduction to abrasive jet machining. So, we move on to one of the process called abrasive jet machining, and we will see jet machining process parameters, and we move on to the input parameters on output responses, the effect, how each input parameter plays a vital role on the output responses, and the material removal models for brittle and ductile materials, applications of abrasive jet machining, and at last we just see a glimpse of abrasive jet polishing also. This particular process also can be used for polishing applications. Okay. So, but the application wise for polishing very less. So, just we see a glimpse, that is all. So, advanced abrasive machining processes, what are the processes that we are going to study in this particular section of this course is abrasive jet machining, abrasive water jet machining, ultrasonic machining and elastic emission machining. These are the mechanical processes where abrasives are used, and there are few processes, but these are predominantly used abrasive processes in the spectrum of advanced machining processes. We move on to the abrasive jet machining. We see, if you see this particular slide, most of the slides which we are borrowed from Professor Vijay Kumar Jain, who is a Professor Emeritus in IIT Kanpur. So, some of the slides are courtesy to him because he has shared the slides with me, and I am very thankful to Professor VK Jain for sharing his slides. Okay. So, when a person hits the ball twice on a wall with F1 and F2, okay, that means that a person is there, this person is hitting the wall with F1 and F2. Whenever if your force is F1 and F2, the crater size or cavity size that is formed is approximately assumed to be D1 and D2. If the force F2 is greater than F1, then D2 will be obviously greater than D2. This is basic physics. Okay. Abrasive jet machining follows like this. and d2 and d1 size is nothing, is a function of kinetic energy of the ball when hitting the wall. That means that this particular abrasive jet machining works on the various input parameters such as how velocity of the abrasive particle is traveling towards the workpiece and how it is hitting, whether the material, workpiece material is a ductile material or a brittle material, so on. Many parameters are there. One thing is that if you just hit with a stone to a particular material, assume that you are hitting a stone to a dry mud. So, what will happen? There will be a crater, there will be a cavity formation on the mud, dry mud. Okay. So, that is the basic concept of abrasive jet machining. Now, we move on, you can, this basic concept we can pile up or compile towards using the abrasive jet machining. So, abrasive jet machining works on this particular principle whatever I explained, where the stone is hit a dry soil or a mud, which is a soil, I mean to say it is not a loose soil, it is a lump of a solid where you have a clay, just hit with a particular stone which is slightly harder than this one, and this clay which is a solid clay. So, it is less harder with respect to the stone. So, and it is a brittle material. So, there will be a crater formation. That basic principle which we will see in particularly in abrasive jet machining. And if you are going to hit this particular clay with force F1 and F2, what will happen? The crater size or a cavity size that is formed on that particular solid clay will be more and more. If you are hitting with low force, small crater; if you are hitting with high force, crater will be very big. So, now based on this particular principle, the people came up with a technology called abrasive jet machining. You can see the abrasive jet machining, normally these are the highly compressed air along with the abrasive particles will impinge which pass through a fine nozzle, and you can achieve or you can cut the intricate shapes like complex surfaces you can do, and you can do a glass cutting or another cutting processes. If you can clearly see here how a particular shape of a glass is cutting using the air and at the same time abrasive particles. The air is considered to be the carrier medium. As you have seen in the previous slide, there is abrasive jet machining, abrasive water jet machining. So, in the abrasive jet machining, you are going to use air or some gas as the carrier medium. In abrasive water jet, you are going to use water which is a liquid as a carrier. In this particular AJM, what you have to note here is carrier medium is air, media or medium is one of the things is air, then gas. You can use inert gases or some other gases also you can use to carry the abrasive particles along the direction of the velocity of the air. The principle, the fine particles normally 0.05 mm are accelerated in a gas stream, commonly used is air at a few times atmospheric pressure. That means that you can use 10 bar, 20 bar, 30 bar, 50 bar, like that. If you can use in terms of bar, people will understand that. So, I am saying bar, but internationally if somebody is watching, assume that if I am going to use 10 bar, that means that 1 megapascal. Okay. So, you can use 1 megapascal, 2 megapascal, 3 megapascal of the pressure of the air, which is a carrier medium, and you just mix the abrasive particles and you just inject on a surface to be impinged. Okay. So, that you can cut the intricate shapes or you can generate the craters as per your requirement. The particles are directed towards the focus of the machining less than 1 mm or the tip, that means normally it is called a nozzle tip distance. Normally you come across all these words in the upcoming slides. You just focus on the workpiece so that you can cut the workpiece. As the particle impacts on the surface, if the particle impacts on the surface with high velocity, this causes a small fracture and the gas stream carries both abrasive particle and the fractured particles away. Okay. So, this what it will do is this gas stream, which is considered to be the air, will carry both abrasive particle and the fractured wear surface away from the this. That means that whenever you impinge, if it is a through cut, so it will carry the debris as well as abrasive particles also. If you see here how the abrasive jet machining works, this is the nozzle. Okay. So, this is the nozzle tip distance, this is my workpiece, which is nothing but the distance between workpiece top surface to the nozzle exit is nothing but nozzle tip distance, and fine abrasive particles plus air is coming here, and this is the crater depth. That normally this is the crater depth that is formed on a surface. So, how you can measure the crater diameter as well as the crater depth. If you see, this is my crater. Crater have its own crater depth, at the same time crater diameter also you can measure. So, depend on your input parameters like air pressure, abrasive particle size, type of abrasive, type of workpiece material, these are all will decide the crater depth as well as crater diameter. This it will decide. If you see the schematic diagram of AJM system, I mean to say previously whatever you have seen is a machining region where nozzle is there and workpiece is in impact, but how to generate this much pressure, how to generate the velocity of into the abrasive particle and other things will come under the complete system. Okay. So, first what you have to require, what you need is a compressor. So, compressor with a relief valve, air filter, dryer and other things. Dryer is required because you do not want any wet condition in the atmospheric pressure. So, the compressed air now will be generated, will be opened, and the opening valve will be there, pressure regulator. This pressure regulator will tell what is the pressure. What is the pressure? That means that output pressure, what pressure? It is the air that is passing here is 1 megapascal or 10 megapascal or 20 megapascal or something, whatever the pascal that will show. Now, it will go into a mixing chamber. This is the mixing chamber where you are feeding the abrasive particles and your gas is compressed gas is coming. Okay. Both will mix and it will come like this. In this area, what is compressed air is there plus abrasives are there. Okay. So, this abrasives and compressed air plus abrasive particles will be there, and this will come and hit on the surface, so that you can generate a crater which have a crater depth as well as crater diameter. Now, once the crater is generated or a cavity is generated, you can measure the crater and the other things, crater diameter as well as. If you see this particular diagram, just whatever you have seen in the previous one is just shown in a schematic way. So, the abrasives are falling on this one and it will generate the crater, which is having two parameters. One is crater diameter and crater depth. Okay. The crater will be generated like this, which will have, assume that if it is like this is the diameter d and this is the depth small d. This will be a crater diameter and this will be crater depth. So like that you can generate the cavity or crater on a particular material. If you see the schematic diagram and the picture, normally you can compress the gas supply, normally air will be supplied. The main motto to show you is how the system look like, and you can also see the practical setups that are developed by some of the IITs also. So the gas supply filters are required to filter out the moisture, filter out the other things and which is unwanted, and the pressure regulator, just you mix the powders here and you can even give the vibrations to it so that you can get more and more mixing at the same time. Once you done, then you just impinge. Now if you can impinge, what will happen? The machining will takes place properly and you can orient your nozzle as per your requirement. Okay, so practically you can see how the cutting action is taking place by the abrasive jet machining. So the same thing you can see here. Okay, so this is the nozzle and this is the machining. Okay, the box which is shown in a schematic is clearly shown in the experimental way. So this is the one of the experimental setup practically that is developed at IIT Kanpur. So again I am very thankful for the professor who developed at IIT Kanpur this. The normally 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it shows hopper for the abrasive, pressure regulator, flow meter, mixing and other things. Whatever if you see here, so this is the workpiece and abrasive jet machining region where the high pressure abrasive mixing is coming and impinging on your workpiece surface, so that the machining takes place, the crater takes place and the material removal takes place. Okay. So what are the systems that you require? What are the components that are what are the components that play a major role in abrasive jet machining? Is one is the gas propulsion system, that is nothing but the supplying of clean and dry air which propels abrasive particles. Compressor are normally required. Now if you want to compress the air for higher and higher, you require a compressor. And the gases which are non-toxic, cheaply available, easily available. The one of the best example is air. Air is considered to be the cheapest and economic one which is easily available in the atmosphere. Then the abrasive feeder, normally the abrasive feeder will have the quantity controlled by the vibration. You can control the vibration and you can control the amount of the abrasive particles that are falling, and you can control these particles, how much particles you require. You come across one word called mixing ratio in the upcoming slides. So there you will see how much abrasive particles that are coming with respect to the carrier medium, that is nothing but the air. Machining chamber, well closed abrasive particles content should be below harmful limit and the vacuum dust collector should be attached. That means that, as I said, these particular things should be carried out at the closed environment, so that the dust particles are, because the ceramic, assume that you are going to machine a ceramic material or a brittle material and your abrasive particles is a brittle, what will happen? There will be a brittle fracture, fragments will come up because the fragments will be a nanoparticles and the surface area is so high that these may come out and causes lot of problems to the operator. So it should be done in a closed environment. The abrasive jet nozzle, so normally sapphire nozzle will be used whose life will be approximately 300 hours, and circular or rectangular cross section depend on your requirement. Assume that if I want to make a hole, I can go for circular. If I want to go for a pocket, some of the applications require pockets on a ceramics or something. In that circumstances, you can go for rectangular cross section or a square cross section and these type of cross sections. Nozzle pressure, normally normal pressure which varies from 2 to 8.5 kgf per centimeter square. When the workpiece material and MRR requirements are very high, then you have to go for very high pressures. Increased wear, stray cutting and high inaccuracy. If you are going for very high pressures and high standoff distance or something, then what will happen? Stray cutting. Normally stray cutting does mean that assume that this is the workpiece and my requirement is cutting in this section. Assume that I want in this particular section only. As if my nozzle is here, the diversions goes like this. Stray cutting means the extra portions, this is which is unwanted, which is called as a stray. So here also you can see here, see unwanted is nothing but the stray. So it is going beyond what I require as a customer or as a manufacturer. If I want 5 centimeters hole, if I am generating 5.2 or 5.3, that extra portion is nothing but the stray. So the abrasives controlled by masking the workpiece. You can control the hole size and other things by masking the workpiece. Assume that the stray cutting, if I want to control in that circumstances, what you can mask it. Assume that I want in this portion, so you can mask the other portions with other material, sacrificial material, so that what will happen, the required portion is exposed and the abrasives will take away the material in the form of craters or cavities. Mechanism of material removal, if you see the abrasives and nozzle tip distance and other things, when the abrasive particle hit, what will happen? It will fracture the material, and the fracture mechanism and other things you will see in the upcoming slides. Whenever this particular abrasive comes and hit, so it will generate the similar converse shape of particular portion of hitting, and it may, if it is a brittle material, it goes out as a brittle chip like this. If it is a ductile material, the material mechanism will be goes by deformation, continuous deformation, then the shearing, chipping and other things will take place in ductile one. Okay. The fishbone diagram shows what all the parameters that are affected by the abrasive flow. What are the parameters that will affect the output responses in the abrasive jet machining? So, first one is a nozzle. Nozzle will play a major role. So, nozzle diameter, nozzle type and cross section of nozzle, as we have seen, 2 cross sections will be there. One is circular cross section and another one is rectangular cross section. The mixing chamber, the length of the chamber is increases, what will happen, what the mixing will be better. At the same time, it may decrease the velocity. Okay. So, the bore diameter, type of chamber and other things, workpiece parameters, normally hardness of the workpiece, geometry details and other things will play a major role. In the abrasives, flowability of abrasives, type of abrasives like SiC, that is silicon carbide or alumina or boron carbide or cerium oxide, and what is the volume fraction that you are going to mix, that means whether you are going to mix 1:1 or 1:10 or something. At the same time, abrasive particle size, whether it is a fine size or a coarse size or a medium size, they like that. And the carrier medium also play a major role. Which type of carrier medium, whether you are going to use air or whether you are going to use argon or which is inert gas you are going to use, and the pressure, how much pressure. If your pressure is very high, what will happen? The indentation will be very high. So, the process parameters such as mixing ratio, how much abrasive particles to the carrier medium that you are going to mix, and the standoff distance, how far your nozzle is from the workpiece surface, and the traverse speed and the pressure. So, these are the input conditions which determines the output responses, such as machining rate, how fast you can do the machining, depth of cut and kerf quality, that means that whether you have achieved a good quality or a bad quality, which is a qualitative one. Okay. So, the abrasive jet machining process parameters, the main 3 parameters, among all the spectrum we have 3 or few more, some people will follow. So, the mostly important one is abrasive particle, which is nothing but the composition, strength, size and mass flow rate of abrasive particles. At the same time, carrier gas composition like air, whether you are going to use, or argon you are going to use, or any other inert gas, at what pressure and at what velocity it is helping the abrasive particles to hit the workpiece. And the nozzle geometry, nozzle material, because nozzle material, as we have seen in the previous slide, that the sapphire is one of the best materials, so that the life will be approximately 300 hours for one nozzle. So, if you are going to use very low quality materials for the nozzle, what will happen? Your nozzle goes off, your nozzle worn out, and you have to go for a new nozzle. So, the non-productive time increases, so the product cost will go up, because your production time will increase for a particular component. The standoff distance is one of the things, that is nothing but nozzle tip distance. Some people, some of the books follow nozzle tip distance, some of the books follow the standoff distance. Okay, the standoff distance and nozzle tip distance is both are same, which is nothing but the starting of the nozzle to the surface of the workpiece. This is nothing but the standoff distance or nozzle tip distance. And the feed rate, at the same time inclination to the work. So, whether you want to go for certain inclination to the workpiece, or whether you want to put it perpendicular, or that is all the parameters that play a major role among the fishbone diagram. You have a complete set, but some of them have huge influence or major influence, some of them have less influence. So, these are all whatever you are seeing in this particular slide are having a major influence on the material removal rate, crater depth and crater diameter. So, the first one is abrasive particles that play a major role. The abrasive should have the sharp and irregular shape. Normally, all the abrasive particles are randomly oriented, at the same time shape is random. One abrasive particle may like this, one abrasive particle may like this, one abrasive may be like this. So, shape normally will not be a constant in this one. The fine enough to remain the suspended in the carrier gas. If you can go for particle size, lower particle size, the suspension or the suspending in the gas is very good, because of the high surface area. It should have excellent flow characteristics, because it should follow the path of carrier gas, so that it will do the required purpose. Al2O3 normally uses for the cleaning purpose, cutting purpose and deburring purpose. The silicon carbide normally uses for similar applications of Al2O3. But for harder material, that means that if you are going to use Al2O3 for softer materials, slightly harder material, if your customer comes with a slightly harder material, then you can go for silicon carbide. And glass beads, you can go for matte finish or matte finish. Sodium bicarbonate normally you can use for the cleaning applications, cutting, deburring of soft materials and other things that you can use. So, abrasive sizes and functions. If the size is small, large and other things, normally if you see here, the size, the abrasive particle size is 10 to 15 microns is the commonly used, because if you are going to use very small, then there will be a problem of agglomeration. That means that multiple particles will come as agglomerate. But normally in this particular gas assisted process you may not get, but in the water jet machining or some of the people will use some of the other liquids also, there the agglomerations will be a problem. So, you should go for a specified particle sizes. Normally small sizes you will use for cleaning and polishing, and larger size will be used for the cutting process. As I said, we see abrasive jet polishing at the last of this particular class, where you will use the fine abrasive particles, so that you can get the polishing operation. Reuse, basically it is not recommended, because it will be contaminated with the chips and may block the nozzle passage and lower ability and lower cost. That means that whenever, assume that I have a abrasive particle like this is very sharp edge is there. Okay. So, whenever you are using a first time, the sharp edge may remove the material, but whenever you use the second time, what will happen? This will become blunt and its efficiency goes down. At the same time, whenever you are going to use it, what will happen? This may accompany by the chip material also. Okay. This chip material accompany. So, the performance of this particular abrasive particle goes down, and the performance goes down by lowering the cutting ability. At the same time, abrasive particles are not that much costly. So, it is economical to go for Al2O3 or SiC. Normally, these particles nowadays are the previously which we used in the 2015 and 16. So, you can get in Indian market like 1000 mesh size or something, approximately like below 500 rupees. So, the 1000 mesh size, up to 1000 mesh size, you can get approximately 500 rupees per kg Al2O3 or SiC, both approximately you can get this particular mesh size for within India. So, some of the companies placed in Agra and these companies provides this type of abrasive particles. If you are going for better abrasives which placed in abroad nations like Germany and other countries, so import and export charges may be come into picture and the cost of the abrasives may go up. For the applications of abrasive jet machining, I guess you can go ahead with this particular thing. I guess you can go ahead with this available abrasive particles in India. So, the second thing which you have to note down is normally the aluminum oxide, that Al2O3, silicon carbide, sodium bicarbonate, dolomite and glass bead, these are the commonly used. The particles, different particle sizes are also mentioned in this one, and this aluminum oxide and silicon carbide are mostly used in the abrasive jet machining for the cutting operation, grooving operation. At the same time, light finishing, if at all I want to go, normally I go for sodium bicarbonate, and which can use for the finishing applications. At the same time, dolomite you can use for etching and polishing applications, and light polishing and fine deburring, if at all you want to go, you can go for the glass beads. Okay. So, that means that in the abrasive jet machining process, if you can control the pressure, if you can vary the abrasive particles, if you can vary the pressure, you can convert this particular process into abrasive jet polishing process also. So, some of the people who are doing masters and wish to do PhD and other things, so you can work this particular thing, that how to convert or how to change the setup or change the parameters to change from abrasive jet machining to abrasive jet polishing. So, there may be very less papers on abrasive jet polishing. So, you can choose this particular thing or abrasive polishing, abrasive jet polishing as one of the topics by choosing dolomite or sodium bicarbonate as your abrasive particles. You use appropriate pressures and you can do on those workpiece materials. You just do some literature and you can get some information and you can move on to a good topic. So, the second one is a carrier gas. Normally carrier gas, it should be non-toxic, cheap, easily available. I can say instead of cheap, you can say economic is a good word to use rather than cheap. It must not flare excessively when the discharge from the nozzle. That means that it should not diverge much. If it is diverged, then what is my requirement will be gone. And commonly used gases are CO2, nitrogen, air and other things. Air is commonly available one. So, the air is mostly preferred due to universal availability and it is non-toxic nature, because rarely we are breathing in. So, air is non-toxic, at the same time it is economic. So these are the nozzles. The third one is the nozzles. You can go for this type of nozzles of various dimensions. You can see all here, multiple nozzles also available, and single big nozzles also available. You can go for this type of nozzles to fit into the abrasive jet machining, and you can achieve your goals. Okay. The nozzle material is most important one. So it has to withstand the erosive action of abrasive particles that are passing by the nozzle, because the abrasive particles are mixed with the highly pressurized gas in the mixing chamber, then it is pushed. That means that these abrasive particles also attack the walls of or the inner walls of the nozzle. So the erosive wear of this particular nozzle should be less. High resistance to wear, that means that it should be wear resistant material that the nozzle is fabricated, and the circular or rectangular cross section, normally you can use the tungsten carbide and sapphire. Sapphire is basically used material. So tungsten carbide if you see and the sapphire if you see, normally the nozzle life if you see here, tungsten carbide is approximately 20 to 30 hours. But here the problem is that you have to replace the nozzle again and again. Assume that average if it is like 20 hours or something. So every 20 hours you have to replace the nozzle. Because of this, the non-productive work or the non-productive cost of your manufacturing will increase. So to avoid that, you can go for the sapphire whose life is 300 hours. Okay. So the changing of this nozzle will be reduced, at the same time the time will be saved and the production rate will be increased. So you can sell the product at the economic price subjected to the cost of tungsten carbide and sapphire. If the both costs are approximately same, then you can recommend to your shop floor people that you can go for the sapphire. So the material removal mechanism, the ductile materials. In case of ductile materials, material is removed by the plastic deformation and cutting wear and plastic strain and the deformation wear. During the impact, when the yield strength of the material is locally exceeded, the plastic deformation takes in the vicinity of the impact. That means that whenever the abrasive particle goes and hit a ductile material, there will be a plastic deformation, and nothing in this world is perfectly flat. So you have a peaks on the surface, so it also shears the peaks. That means that it will remove the material by shearing action also. So after multiple impacts, plastically deformed surface layer may form a near eroded surface, and therefore the yield strength of the material increases due to strain hardening, and upon further deformation the yield strength at the surface of the material will eventually become equal to the fracture strength. No further plastic deformation will take place and the fracture will take place. At this point, the material surface become brittle and fragments may be removed in a subsequent impacts. That means that if you are going to impinge, because the millions and millions of abrasive particles which are carried by the carrier gas impinges on the workpiece. So plastic deformation, strain will increase, and the plastic deformation still goes on increase, and fracture will takes place. At certain position, what will happen becomes the eventually yield strength will become the fracture strength, and the fracture will takes place in the material and it will goes out as a chip. Okay. This particular point you have to note that the yield strength increases and it will reaches to the fracture strength, and the fractured material will goes off as by leaving a cavity there. So material removal mechanism, normally whatever you have seen in the previous slide, that is for ductile material. If you are going for brittle material, what will happen during the brittle material erosion process, the particle impact produces different types of cracks, and the chipping is due to brittle fracture and negligible plastic deformation. Okay. So whatever you are seeing here, there is a plastic deformation is taking place for the ductile material. and whatever you are going to see here is for a brittle material. If there is a impact is coming and hit on the surface, there will be a cracks, and this will eroded material will remove the material in the form of a fine chips. So, that means that for the abrasive jet machining, the best suitable material to remove material is the brittle materials. So, nozzle tip distance versus cavity. If the tip distance increases, what will happen? The cavity diameter will increase and the depth will decrease. If you see here, this is a schematic for your better understanding, and if you see here, so your diameter 1, G stands for nozzle tip distance and G2 stands for the increased nozzle tip distance, goes on increase, then your diameter will increase, but your depth will decrease. Okay? That is what we want to convey from this particular slide. Effect of nozzle tip distance on the cavity diameter. In the cutting nozzle positioned by very closely to the workpiece, normally the distance is 0.8 mm. At the closed nozzle tip distance, cutting rates are compared for the sake of increasing accuracy. That means that whenever the nozzle tip distance is low, that means that your interest is to get the perfect cut or perfect dimensions that you want. Okay. So, the accurate dimensions that you want. If the nozzle tip distance eliminates the taper and minimize the curves whenever you are going for smaller distances. The typical divergence angle normally will be 7 degrees for the air. If you are going to increase the nozzle tip distance to 5 to 12.5 mm, abrasive jet stream become widened and used for the cleaning and pinning application. That means that, so at higher distances, what is happening here is it is not going to do the machining operation. However, it is going to do the cleaning operation or the pinning operation. Okay. The light duty operations such as glass frosting are accomplished with the normally the nozzle tip distance beyond 25 mm. So, whenever you want to do the glass frosting and other things, you just go for far away distances like beyond 25 mm, so that it will do some texturing on the surface of the glass. So, some of the people who want to take up the research areas for texturing of the brittle materials, then you can go for abrasive jet texturing process also. So, the parametric analysis, if you see abrasive flow rate, the maximum observed normally high abrasive flow rate will lead to high material removal rate. The more cutting, higher MRR. If the abrasive particle size is very big, the cutting action will be very high and material removal will be very high. And low abrasive flow rate, normally what will happen? The low MRR due to less cutting edges and other things. Nozzle tip distance, as I said, if your nozzle tip distance is low, you can use for cutting purpose. If the nozzle tip distance is high, you can use for cleaning purpose or pinning purpose and other things. If the nozzle pressure is very high, what will happen? The material removal rate will be very high. If the nozzle pressure is low, what will happen? You can use for cleaning or texturing applications and other things. Just the mixing ratio. So, the other keyword here is the mixing ratio, that is nothing but the volume flow rate of the abrasive particles to the volume flow rate of the carrier gas. That means that you have two things here, one is the gas, another one is the abrasive particles. If the mixing ratio is very high, that means that your abrasives are higher in number compared to your carrier gas. Okay. So, an increase in the value of M, that is nothing but the mixing ratio increases volumetric material removal rate. Normally, some people represent MRR, that is nothing but material removal rate, and MRRV represent volumetric material removal rate. See here it is shown MRRV, that nothing but it is volumetric material removal rate. But large value of M may decrease the jet velocity and sometimes it may block the nozzle also. If you everything has its own limitation. If you are going to use more and more abrasive particles, what will happen? The abrasive particles collide each other and they lose the original velocity at which they have to travel, and it has to hit. At the same time, there is another problem that these abrasive particles may block the nozzle. So, if the more amount of abrasive particles are there, it will be a disadvantage. So, always as a manufacturing engineer, you should think about the optimum mixing ratio, so that you can get you required function, that is whether it is a machining, whether it is a cleaning or pinning or something. So, volumetric flow rate of abrasive to volumetric flow rate of carrier gas is nothing but the mixing ratio. Normally, mass ratio also is there, that is nothing but mass of the abrasive particles to combination of mass of abrasive particle with carrier gas. So, volumetric material removal rate, if you see here CF theta MVN, which is given by the Finney in 1960, where C and N are constant and the flow stress of the workpiece is also given here. So, the flow rate, if you see the output responses, that is how the abrasive jet machining works, the MRR increases only up to certain value. Then if the abrasive flow rate increases, as I said, what will happen in the phase 1, as you increase till 12 to 16, what will happen, the value of the material removal rate will gradually increases, because if the abrasives are more, what will happen, the number of times of abrasive particles will hit will be very high. So, the craters formation will be very high and material removal will take place. If you beyond certain value, if you are going to increase the abrasives, what will happen, the abrasives will hit one another and its velocity will be reduced. The abrasive flow rate increases, the number of abrasive particles cutting workpiece also increases, thereby material removal increases. This refers to part 1. Okay. However, with further increase in abrasive flow rate, the abrasive velocity goes down, because in the section 2, what will happen, the abrasives try to collide each other and there will be a loss in the velocity. At the same time, this may also clog the exit of the nozzle. If it is partially clogged, then that means that the velocity at which it has to come may be completely disturbed. So, you have, that is the cause for the second portion. So, the material removal rate will be decreased if you are going beyond certain values. So, from this particular graph, what is the inference is, people can go approximately, this is the values where one can use for optimum, like you can go for 10 grams per minute, maximum to 16 grams. If your material removal rate is good at 10 grams per minute, so you can go for 10 grams per minute, so that you can achieve the better material removal rate in this particular context. So, if you see the other parameters, normally nozzle tip distance, if the nozzle tip distance is increases, what is happens here is, the crater diameter will, if the nozzle tip distance is low, what will happen, the material removal will be good. If you are going to increase beyond which, what will happen, the crater depth will reduce, but crater diameter will increase. But whatever the problem here is, if you are going to increase the distance between the nozzle and the workpiece, what is going to happen here is, the velocity, it loses the velocity. As the distance is d1, if you go for d2, what is going to happen is, it loses its velocity. So, the losses will be there because it is coming into the atmosphere, the pressure difference is there. Because of the pressure difference, the velocity will lose. If your mixing ratio is high, that means that abrasive particles are high, normally what you are going to expect is the curve will move like this. Okay. Beyond certain value, again it will goes down, because as you have seen the same reasons in the previous slide, that it decreases the velocity and it may block the nozzle also. If you see here mixing ratio with respect to nozzle pressure, that means that how much pressure you are increasing. If you are increasing the pressure, the jet will come and hit with high velocity. For that purpose, the material removal completely increases. At the same time, if you are going to increase the mixing ratio, obviously the material removal increases. If the nozzle pressure increases, what will happen? The velocity at which the abrasive particle hits will be very high, and the crater size will be very high, and the material removal volume will be very high. Mixing ratio, as you have seen in the first slide, that mixing ratio, if your mixing ratio is up to certain value, like what the 10 is the value, if it is increases beyond which it blocks, and internal collection of the abrasive particles will lead to the pressure, velocity decrease, and other things will takes place. If you see the standoff distance, if the standoff distance is increasing for the mixing ratios, here you can see the mixing ratio 2. Previously whatever you have seen is a qualitative things, those are taken, but if at all correct values are required quantitatively and other things, better material removal is achieved if your mixing ratio is very high. At the same time, for the nozzle standoff distance is approximately 16. Okay. For this particular thing you can achieve better value. So, the mixing ratios are ranged from 0.05 to 0.268. So, the mixing ratio, that means that abrasives are increased. If the abrasives are increased, normally the number of craters generation will be also increased. Okay. So, the material removal obviously increase. If the standoff distance is increased, if the standoff distance is too less, what will happen? It do not have sufficient velocity to carry. So, you also need the standoff distance a optimum value, so that you can hit the workpiece. If you see the standoff distance with respect to volumetric material removal rate and the penetration rate, is the penetration rate. If the standoff distance is too low, then normally the penetration rate is also somewhat low, but if your penetration rate will be slightly increased if you give sufficient space or to the nozzle. If you give sufficient space to the nozzle, what will happen? It has certain distance where it can carry the velocity and hit the workpiece. For that purpose, normally the penetration rate will increase, and beyond which the penetration rate will decrease. If the penetration rate decreases, what will happen? The volumetric material removal also will go on decrease. That is what you can see in this particular slide. So, nozzle pressures with volumetric material removal rate. Here you can see all the values. So, previous slide, similar slide you have seen, but the thing is that there it is a qualitative one. As you increase, it will increase, but how much increase of the input parameter will increase the how much output response, that we are going to see here. Here 0.143 mixing ratio gives the highest value, that means that mixing ratio is high. So, the higher material removal rate is achieved for the higher nozzle pressure. If the nozzle pressure is 30, you are getting the higher value. So, if your nozzle pressure is very high, so the impact will be very high. That means that the abrasive particles will be hit with the high velocity. So, the material removal will takes place. That means that the nozzle pressure, that is volumetric material removal, is shown in the one. What is the kinetic energy of abrasive particle is responsible for material. So, if your nozzle pressure is very high, the kinetic energy of the abrasive particle will be very high, and the material removal rate will be increased. Now, we see about the material removal models for the brittle and ductile materials using abrasive jet machining process. Material removal model for the brittle materials. This is proposed by Nilima and Pandeji, Professor Pandey. So, assumption material removal by normal impact only. That means that there is no additional things involved. So, abrasive particles hit the workpiece and the workpiece material will be removed. That is a simple assumption. So, MRR is taken in kgs per second. So, 0.1156 P A, MA and VA square. So, by upon 103 sigma FW, where PA stands for abrasive particles density, or MA stands for mass flow rate of the abrasive particles, VA is the component of particle velocity, that is, and normal to the work surface. That means that assume that my workpiece is like this and my jet is like this and abrasive particles are coming and hitting perpendicular to this particular surface. Okay. So, this is how it is, and sigma Fw is the flow stress of the workpiece material, the normally what are the flow stress of this workpiece material. Okay. These are the abrasive particles and this is the nozzle from where the so this is normally what Professor Pandey has proposed for the brittle materials. Okay. So, if you see the material removal model for the ductile materials, as you have seen, this particular process is mainly suitable for the brittle materials because abrasives are coming and hitting. So, the fracture and small fragments of the chips, then it will goes off. That is the most major mechanism, or this is suitable for the brittle materials, but people have used for the ductile materials also, as I discussed in the previous slides, that where the flow stress will be equivalent to your fracture and then it will goes off as a chip. So, in the same way the ductile materials also proposed here the material removal model. Sheldon and Kenhere is proposed the model for MRR for the ductile materials. If you see MRR in the volumetric material removal, normally K1D cube and VA cube and divided by where the various terms are given here, the rho A and HVW, this is the one equation. So, where K1 is a constant of the proportionality and DEM is the mean diameter of the abrasive particle or abrasive grain. VA is the volume of importing particle, that means that how much material is going away, and rho A is abrasive particles density, that is kg per mm cube, and HVW is the Vickers diamond pyramid hardness number of the target material. That means that indirectly you are saying about the hardness of the workpiece material, and the amount of material removed is related to the depth of penetration of the particle. That means that how much particles are hitting, it generates the deformation, then and prolonged abrasive particles will hit, then the fracture will be removed. So, that is what the amount of material is removed related to the depth of penetration. That means that how much penetration is taking place in the workpiece material will be taken into consideration for this particular model. These are the two mathematical models that are proposed by different authors. So, this may be useful for the people who want to do some of the possible research or some of the relative research. If at all you want to move ahead with this particular model, you can move ahead also as considering these equations as the base equations. The process capabilities, if you see the low MRR, normally 0.015 centimeter cube per minute is the material removal. So, intricate details and hard and brittle materials can up to for the lower material removal rate. That means that normally if at all you want to do the abrasive jet machining for intricate shapes, then you don't bother about much MRR, that is material removal rate, because the intricate shapes it has to go and it has to do. So, for that purpose you don't look for the material removal. That is why the material removal is very low for that one. Narrow slots, you can cut a narrow slots normally 0.12 to 0.25 mm slots you can cut using abrasive jet machining. You can achieve low tolerances ranging from plus 0.12 to minus 0.12 microns you can achieve. And the good surface finish, normally from the nano surface point of view, this is not a good value, but for the machining purpose, the surface finish that you are going to get is minimum is 0.25, which is a good surface finish from the finishing point of view. But this particular process is dominated by the material removal mechanism, that is nothing but it is a machining process. That's why we are considered this abrasive jet machining as one of the advanced abrasive machining processes. So minimum radius that can be produced is 0.2 micrometer. So this can produce a good amount of radius. Okay, so process capabilities, still there are some more process capabilities. Steels up to 1.5, glass up to 6.3 mm thickness you can cut. That means that if at all you have a steel plate of very small thickness you can cut, or the glass plates with big thickness you can cut using the abrasive jet machining. Thin sectioned brittle materials, inaccessible areas can be machined by this particular AJM process. So these are the capabilities of abrasive jet machining process. Almost no surface damage because there is a gap between abrasive particles. At the same time, heat generation in this particular process is normally low because you have air which is a lubricant or which act as a coolant in this particular action of the abrasive jet machining, and there is no surface or subsurface damage. In the thinner materials, taper is 0.005 inch per inch of the material thickness. That means that normally if you are going for 1 inch, 0.005 inch is the taper that normally observed. So this is, if the requirement to the customer is very minimal, then you have to think about some other processes. If this is within the limits of their requirement, then you can go for abrasive jet machining process. No taper can be tolerated in the cutting edge, so the nozzles or the workpiece can be sometimes tilted to the component compensate this. That means that, so if at all you don't want this type of tapers, then you can tilt it. Nowadays you can tilt the nozzle, assume that this is your nozzle, you can tilt as per your requirement. If at all you don't want, assume that some microns taper is coming, just you move your nozzle or you give some tilt to your nozzle in opposite direction of that microns so that you can compensate it. This effect of negative taper or the part double the taper than scrap. That means that you can improve, and if at all you want the tapered holes or something, then you can use obviously this particular process with slight experience and other things. Advantages of abrasive jet machining: if you see, the ability to machine heat sensitive, brittle, fragile materials. That means that if it is heat sensitive material, assume that when any materials are mostly subjected to heat sensitive, then those can be machined by abrasive jet machining because this particular process don't develop any heat during the machining process. Okay. Very little or no heat generation due to non-contact cutting and microscopic material removal. That means that the material removal is very minute. At the same time, non-contact cutting tool, that is nothing but you have abrasive particle, in between there is a air gap. So air will act as a lubricant or a coolant or something. So it is a sufficient time or a ample time is there between one abrasive particle to another abrasive particle if your mixing ratio is slightly less. So there won't be any generation of heat in this particular process. So low capital investment and low power consumption. That means that you can develop this abrasive jet machining in your laboratory with a very minimal cost. That means that if you don't have funding also, you can develop. You need a one compressor. So normally compressors are not that much costly. So you can have different ratings of compressors, and you can get those compressors. Then you just put a feeder, abrasive feeder, and you can mix it in a mixing chamber and just impinge on the workpiece. So you can start your basic research with low investments, which assume that if your institute or university can give a minimum amount of some amount, a minimum amount if they can give, then you can develop this abrasive jet machining, and power consumption also very less. So I think the universities will higher authorities of the universities will allow you for going ahead of this particular process. No part chatter or vibration is observed because there is no chance of vibration. So if at all, what you have to do is you have to firmly hold your workpiece, so that if at all there is anything such small minute things are there from the point of chatter or something, then can be avoided. So machines are very hard, it can machine very hard materials. That means that hard to brittle materials, normally brittle materials are hard materials also. So you can do the machining of these hard materials. Disadvantages of this particular process: nozzle wear rate is very high. As I said, you have to go for sapphire. If you go for sapphire, normally you go for 300 hours. Okay, if you are going for the tungsten carbide or some other things, then now it will be reduced by 10 times. That is, maximum you are going to get is 20 hours or 30 hours. Abrasive particle cannot reuse. That is the biggest problem, because these abrasive particles once hits the workpiece, it loses its cutting edges. At the same time, assume that I have a sharp cutting edge here. So after usage, what will happen? This goes off. So that means that it will become blunt. At the same time, this will catch up some of the chips of the workpiece material, and these chips are hardness compared to the tool material, that is abrasive materials. For that purpose, what will happen? You cannot reuse in most of the cases. It cannot use the machines for soft and ductile materials, because whenever you use the soft and ductile materials, these abrasive particles go and indent. Sometimes it will stay also. So assume that I have a soft material here, abrasive particle can come and hit the workpiece and can stay like this only. Okay, it will stay like this. So in a soft material, this is the biggest problem. Okay, so you may not recommend this particular abrasive jet machining to machine soft materials. Sometimes additional cleaning operation is required on a machine part, because if assume that some of the indentations are generated or some of the abrasive particles are stayed there, so you need a post processing, that is nothing but the cleaning. Stray cutting and machine accuracy is poor. That means that because of the divergence, assume that my nozzle is here, because of the divergence, what will happen? The stray cutting also will take place. Assume that I required only in this region, so I am getting a stray in this region, okay, which I don't want, because the air is a gas try to expand. Because of that problem, the divergence will stay and the stray cutting will takes place. Because of that, what will happen? Accuracy of that particular hole or accuracy of that particular part which has to be generated will go beyond what the customer require. So the customer has every chance to reject that particular part. The process tend to pollute the environment, because abrasive particles are brittle materials. So whenever the abrasive particles are hitting the hard materials of the workpiece, hard workpiece materials, so it will generate some dust. Like gas is there, already you have air plus abrasive dust. Okay, this will lead to pollution. Okay. Okay. So low material removal rate, at the same time the short nozzle stand up distance when used for the cutting purpose. That means that if at all you want to go for cutting, so you have to use nozzle tip distance or the stand up distance very low. Okay, this has to be taken care if at all you are going for a cutting operation. If you are going for a pinning operation or surface cleaning operation, you have to go for high stand up distances. Applications: if you see the applications, normally silicon or tungsten carbide, configuration requirement for AJM for the trimming of electronic components. At the same time, you can use AJM trimmed for the silicon. You can use at the different angles. Okay, you can use at different angles for trimming application. This is one of the techniques that you can use. AJM is successfully employed for manufacturing of small electronic devices consisting of 0.38 mm thickness silicon wafer brazed to 0.75 mm thickness tungsten disc and other things. You can use for the brazing, then you can do the trimming also. After the two materials are brazed together, the silicon wafer must be trimmed and beveled without harming the tungsten disc, and AJM nozzle mounted and desired angle and directed slowly rotating part, and unwanted silicon is trimmed off for the part. Okay, that means that you can trim off as per your requirement. This is one of the special thing about this particular process. Okay, the applications, if you see the applications, as I said, you can see the capability, how beautiful capability by drawing or by creating some sculptures on eggshells. So eggshell is too brittle material on, and it is a very thin material also. So if you can generate a beautiful sculpture on top of it, that means that it has tendency to not break any type of original brittle materials. So that means that it is very superior process to make in a brittle and thin sections any type of sculptures. That means that this particular AJM has ability to machine intricate shapes into brittle workpieces with low thickness. At the same time, you can see some of the metals that are being cut using this. So thin sections also you can go. If you see this particular workpiece material, see how much thick it is. So you can cut the thick sections, you can cut the thin sections. At the same time, you can cut multiple types of geometries. Okay, so some of the geometries you can cut, like some of the complex geometries you can cut on some of the thick sheets also. It is used to drill and cut the hardened metals. Normally you can do the drilling or cutting of the hardened metals also can be possible. It is used for machining of brittle and heat sensitive materials like glass, quartz, sapphire, mica and ceramic. These are some of the advanced materials where you can generate, where you can make without any heat generation, so that if these are heat sensitive, it may change its metallurgical structures, morphological structures or something. So if at all you don't want all these metallurgical changes which are changing with respect to temperature, you can use for this particular abrasive jet machining, so that won't be any heat generation, because of which there won't be any changes in the thermosensitive materials. It uses the manufacturing of electronic devices, which we have seen in the advantages. It is used for the deburring of micro holes also. So if there is a burr, assume that this is my hole on a surface, there are burrs, so you can use by some tilting of your nozzle, you can remove the burrs. Okay, this type of applications also you can use for this type of deburring applications also you can use. This type of deburring applications also can be done by the abrasive jet machining process. So some of the applications, as you can see, the butterflies, dendrite structures, cycle structures and gears can be manufactured. At the same time, many complex shapes with the thin structures and as well as thick structures can be made. Okay, thin as well as thick structures one can cut using the abrasive jet machining process. Okay, stainless steel workpieces, you can see the good and complex structures are fabricated. At the same time, thin structures and mild steel also can be cut. You see the thickness of this particular material, it is too thick material, and you can cut using abrasive jet machining for this particular material. Some of the people might have used by abrasive water jet machining also. These are the same applications, and if you see the applications, removing of the flash parting lines of the injection molded parts can be done, and deburring and polishing plastic, nylon, Teflon components can be done, and the cleaning of metallic mold cavities which otherwise may be inaccessible by other processes can be done by this abrasive jet machining process. Cutting thin section fragile component, that is brittle components made up of glass ceramics, can be machined using abrasive jet machining. Removing of the glue paint from the paintings and other leather objects can be easily fabricated. Frosting interior surface of the glass tubes, normally if at all you want to generate some textures, can be done by using this particular process. Manufacturing of electronic devices, as we have seen, the silicon and other things can be done or trimmed by using this abrasive jet machining by giving some tilt to the nozzle. Permanent marking on rubber stencils can be done by the abrasive jet machining, and drilling of on glass wafers, titanium and other foils can be done. Marking and engraving and glass frosting is another application of this one. So, other part I just want to touch here is abrasive jet machining. You can manipulate or you can modify to abrasive jet polishing also. So, just I am going to give you one or two slides of the glimpse. Abrasive jet polishing process was the first introduced by Finale in the Delft University. Their research showed that this is feasible to utilize abrasive jet polishing for the precision optical manufacturing. And abrasive jet process, they polished BK7 optical glasses, and RMS values are decreased from 350 nanometers to 25 nanometers. That is the best value that they have achieved. So, that means that if you are looking for the abrasive jet polishing techniques, it will be also can be done, but make sure that BK7 is one of the brittle and material. Okay. So, Hirohuchi also made such research on abrasive jet polishing process, and these are the some literature that I am giving, because not much research work is done on abrasive jet polishing. That is why you can go through this particular thing, and if at all some people want to take up or modify the existing abrasive jet machining process to abrasive jet polishing, that can be done, and the roughness values are 1.49 nanometers, and can be done from the surfaces also. Okay. The summary of this abrasive jet machining can be summarized like this. Advanced abrasive machining processes, I just give you what are the processes that I am going to cover in this particular section. Introduction to abrasive jet machining, then abrasive jet machining process parameters, what are the input parameters, and what is its influence on the output responses. Effect of input material removal models for brittle and ductile materials, applications, as well as at the same time I have just touched the abrasive jet polishing. Okay. So, this is about the abrasive jet machining process. Thank you for your kind attention, and we will see the next process in the next class. Thank you.